Hello reviewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about manufacturing of neodymium magnets. So let's dive deep into it. So basically how these puppies are made, this sort of puppy. Now these are permanent magnet and they are made out of neodymium iron B. So NdFeB. And this is also called NIB sometimes. So it's a permanent magnet category made out of 3 core elements that are acting as an alloy, not a compound, alloy. And it's a rare earth element type magnet. There are categories of stuff that we call rare earth. Now, are they actually rare? Ironically, no, they are not rare. They are freakishly hard to find, meaning any mine that is working anywhere on the planet generally has some rare elements. Then why don't we mine it? It's nigh impossible to extract. That's the issue part. And heck, not even extracting the minerals itself, separating between each of them is very difficult. So it's a very, very expensive, and on top of that, idiotically toxic to do. Like the amount of chemicals that this process consumes, you'll be like, I don't want it, let this be rare. That's how toxic it is. So it's a rare, because it's very hard to mine and isolate. In terms of earth crust, we got more than enough. Like if we really figure out a good, efficient way of mining this puppy, it will be like same. Back in the days, aluminum was more expensive than gold. Now we don't even give a damn about aluminum. Same thing. So why the heck we focus so much on neodymium magnets? Well, strongest permanent magnet. To give you some context, you can achieve 1.2 Tesla. Now, how big is that number? Think of it this way. You can get good MRIs at 1.5 Tesla, and that puppy requires superconductor. So the moment you start to measure something in Tesla is serious. Let that be very clear. Like, of course, I do not mean this magnet. You still have to have enough mass there to have that sort of field strength, but it can be achieved, which is, it's flat out impossible with other stuff. So 1.2 Tesla is bonkersly high. So that's there, and its corrosivity reaction is also very, basically resistance is very high. What does that mean? That corrosivity, whenever you are talking about magnets, means basically how resistant it is to demagnetizing. Meaning, imagine you put these puppies in your rotor, it's rotating, okay? Now stator is acting on it. That means there is a fight, action equals reaction. There is a bit of fight. You are pulling it one way, there is a bit of reaction. Over time, it will demagnetize it. Now, how quickly that happens, that vector is corrosivity. Basically, how resistant the crystal lattice itself is to change. Basically, you want a lattice that is like, no, I will stand firm, I will not change. And neodymium is genuinely good at that. So this puppy, this crystal lattice is really good at that. And it's also very temperature tolerant. Now be mindful, we do have selenium magnets which are even more temperature resistant, but these puppy, compared to ceramic magnets, compared to iron magnets, these are good. Like in terms of temperature, it will make all of those look like small, as in like you can buy, like if you have a little bit of money, you can buy magnets that are capable of surviving, let's say 150 degrees Celsius. If you have a bit of money, you can go up to 200 degrees Celsius. Selenium, that puppy goes to 700 degrees Celsius. But it is very good. Like for more than enough scenarios, it's like shut up, take money. So it's very powerful, it's very resistant in terms of degradation, in terms of temperature. It's almost perfect. Like as of now, when I'm making this video, there is nothing that has the balls of neodymium magnet. Like that's a tiny neodymium magnet on a metal table, and that's a big ball, and it's like even bigger ball, one extra ball, and it's like, I got this. That tiny magnet is like, I got this. That's how much flux density this puppy is at. Like it's ludicrously powerful. Like even this, like I'm actually scared if I put my finger in, pinch them, and yes, it has pinched me where it has like actually, it's painful. So this is a very serious thing when we are talking about neodymium magnets. It's very important, very powerful, very resilient, very robust. All of these awesome things. So how do we start? We start with making a powder. So we melt all of the metal. Now you will look into this and you're like, wait a minute, it looks like the guy is going inside a furnace. Well, it's a double wall system. So furnace is there below his foot. This is a chamber wall. So once he put all the material there, he'll seal the chamber and pull a vacuum there. Now why is there? Well, you have to make sure neodymium is one of those naughty puppy that keeps reacting with oxygen like there is no tomorrow. Like iron reacts, neodymium eats oxygen. So you have to make sure, basically, if you do not do that, you will waste majority of your powder. Like all your powder, poof, gone. So we have to do melting in vacuum. So vacuum induction furnaces are used that allows you to melt everything without oxygen. So that's the first step. Then liquid is dumped, basically that liquid metal is dumped on the cooled roller, meaning if you see inside, there is this roller, that roller has a lot of liquid, as in like water flowing through it and spinning, and you pour liquid metal on top of that. That instantly tries to freeze it as quickly as possible, and then it becomes flakes. So flakes forms into it. Now of course the flake would be longer, so there are vibrators that breaks them, but you will make flakes out of it. So that's at the first two steps. You took a material, you molten it, so you got it into alloy state, you made it into flakes. Now that flakes is not powder enough, it's flakes. How the heck you make it into powder? Well, you dump it into hydrogen decapacitator. Yeah, I have no idea what's called. It's very decapitator, basically that puppy. So you dump all of the stuff into a pressure tank and you put GG amounts of hydrogen in pressure. Now why hydrogen? Well, hydrogen has this naughty puppy habit where it's like your crystal lattice, hydrogen, it goes through it. So if you have high enough pressure of hydrogen and high enough temperature, it will take this and turn it into almost pure powder. It will literally break apart crystal lattice. So it's really a destructive way of non-destructively poofing this into powder state. And then that itself does not give you the micron scale powder that you need. Then it goes to another stage where we have jet milling. Basically you have two counter jets using gases and going super duper hyper speed and colliding with each other and turning into dust. So that's how you get that powder stage. So that's how you start. This is your first stage. Then we go to the molding phase. So molding phase, basically whatever you see like this, we start with this sort of mold. Now be very mindful, the molds are generally much larger than what you're gonna get. So for example, if my aim is 1 centimeter cube, the mold could easily be 2 centimeter or maybe even more than that. So you have to, it always starts with much larger. Then you pack that puppy, you put them in a hydraulic press and you pack that puppy, that pack powder, because again if you just drop the powder it will have too much void space, so you pack that puppy. Now to help in that, you pack it using magnetic field, meaning there is a magnetic field and that magnetic field is the preferred grain structure, so you always have to trace it. It's like how exactly it's being magnetized. So you take that, you take the powder, you put magnet. Is that magnetizing it? No, not yet. All it's doing is helping the grain. Basically it's locking the grains. It's like, hey, how about the grain? Because again there's a lot of energy there. Hey, how about you rotate in this direction? You're just, you know, helping things along. So now you have a big block that you have powder compressed it. Now you take that stuff out. Of course, generally at this point it will be completely vacuum sealed. Then you dump it into oil press. So it's like how submarines are tested. You take a giant tank, very thick wall tank, which is filled with oil. You dunk these magnets and you pressurize that puppy. So that you get isostatic pressing. So what is the benefit of that? Now it shrinks even more and the void space in between grains goes down to almost zero. Meaning at this point, you have the highest density that you can viably, economically achieve. So now you have the final magnet. At that point in time, you go in Stirling stage. Basically, I'm saying steaming stage. I have no idea how to say this. Basically, you cook this puppy. Now, cooking is, it also shrinks at this phase also, but this is the final locking, meaning this is ready to be a magnet. So you put it in and be mindful, the temperature and how long it stays in the oven defines the strength. You, of course, control some of the properties by alloying stuff, because be mindful, while we do say neodymium and we do say bronze and we do say iron, there are also spicy stuff. That spicy stuff controls some other vectors. Here, how long you cook it, that defines how much strength you're gonna get. For example, if you are making N32 or N40 magnets, you may only require to cook this puppy for 40 hours, and not 40, 24 hours. But if you're on N52 magnets, you may have to do it for 48 hours, and that's why the N52 magnets are so expensive, and that's why not everybody makes N52 magnet. It takes so much more energy that it's like it may not be worth it. So you pressurize it, you grain lock it, and you cook it, and that's permanent. That makes it into basically ready magnet. The magnet is ready to be magnetized. That's your final product. At this point, it's as ready as it's gonna be. So now let's talk about the final stage, that is machining stage. Machining is basically you take the block that is ready to be a magnet, you grind it down, cut it, whatever you have to get it to final tolerance. Now tolerance will depend on the cost that you are willing to spend. For example, this sort of puppy has tolerance of 0.5 millimeter plus and minus. Generally bit better would be 0.05 percent plus and minus, and then you will have same thing. 0.005 millimeters plus and minus, that's like very high grade. So that will be done in this stage. This is the final. This is the end. After that, you will do plating and coating. And of course, you will compensate in the machining stage if you are very serious about the tolerance. And why coating is important? Here's the deal. Magnets, again, is not a molten alloy same way other things are. So other things, even if they are corrosive, like even if they corrode with oxygen, if they corrode from outside in, this puppy, because it's a powder, even though all the compression reduces the surface area, it does not goes to zero. So oxygen does have the ability to go inside, and it can rust a magnet in like months. So a magnet that could easily last with good coating 10-20 years will barely last 5 months. So oxygen is flat out death sentence for this puppy. So we have so many coating options. Like if you are in a very corrosive environment, you may use gold coating. You are a bit poor, you may go into silver coating. Or if you are like a simple toy magnet, then you will have nickel coating. Now be mindful, nickel coating is not just nickel coating. So you have nickel coating, then you put copper coating, then you put another nickel on top of that. It's like, why? Yeah, that's how many layers they have to be. Make sure then it's damn sure that it's gonna be like completely sealed. And be mindful, copper itself is vulnerable. So copper is almost like a sealant layer. So that's how we achieve basically sealing. And then you can have zinc coating, or if your cost basically if your requirement has that. Epoxy coating is very desirable for many scenarios. Then you have black zinc. Again, I have no idea, but again, you may require it. So that's there. And be mindful, grades of magnets are very kind of easy to understand: 35, 38, 40, 42. And these are zones. These are not precise values. So if somebody says N45, does not mean exactly N45. N45 is the range. So your magnets could be anywhere. But if it's from a branded manufacturer, if they are not trolling around you, it will be good enough where it's like if you design your computer simulation to work on N45, your real world should match that, at least within some tolerance. So you have N45, N48, N50, N52. Now this is just the normal thing that people talk about. So I bought this, so I looked for N52. Yes, it was very expensive. And then we have another grade that is for temperature. So if you have noticed about 3D printers, they talk about, right, if you go above 80 degrees Celsius, it will demagnetize. That means the magnet is N class. N class is normal. Then you have NM class that allows you to 100 degrees Celsius. Then you have HN, for example, let's say you are talking about drill motor BLDC, and you know it's going to be used, it's going to be abused. You may be like, hey, the motor itself heats up to 100 degrees Celsius. We do want some buffer. So you may be like, hey, 120 degrees Celsius magnet. What about EV motor? Because again, if it's a high performance system, you are cooking that puppy. You may be like, hey, let's give some serious room and let's buy a magnet that is 180 degrees Celsius. Which is NUH class, super expensive. So same it goes, like the highest you can buy is NAH. So those last three classes, those are generally used for wind turbines. I have no idea why wind turbines needs magnets that are that temperature resistance, but they do, and that's how majority of those are consumed. But be mindful, those generally have lower power, so they will drop down from N52 to N48 or maybe even N42. But if you need temperature resistance, you have to use, because if you used N52 there and do not have temperature resistance, that magnet is going to be cooked in 1 minute. So what's the point? So you select your coating, you select your grade, all that jazz is done. Then you magnetize this puppy. Now magnetizing requires big current, not voltage, current. You're going to dump some oomph into this, and we have a specific unit of measurement to describe what kind of oomph that you're talking about. That is kilo ampere per meter, basically Ka/meter. So if you are starting at the lower end, you are talking about 2790 kilo amp per meter of oomph to magnetize this puppy. And at the higher end, it can easily touch 4780. And be mindful, some designs require even more oomph than this. So 5000 is easy. If you're buying an industrial grade magnetizer, it will classify that, yeah, I can easily reach 5000. So again, a size of magnet also matters. So machines, this is the final stage. This is where you take your powder, you cook that puppy, and now you have magnetized it. Now you have a full magnet, which you will select which grade it is, which tolerance it has, like whatever have you. All these processes, all these three stages directly give you the result that you buy. Now we come to the naughty part of it. It's the supply chain. So supply chain is almost like oil, where it's like everybody needs it. Nepal needs it, India needs it, China needs it, everybody needs it, but only few make it. Now, this is a very weird thing. Why only few make it? Like silicon technology is genuinely complex, like genuinely complex. Etching something that has few atoms across, yeah, that's complex. But why this? Like if you looked into the process, nothing in it is like high tech. We figured this puppy out in 1990s. Nothing in there. Like if you have the technology to weld metal, you are almost there. Like you can build everything you need to. If you have basic motor, you're good. You can do it. So why don't we? Well, there are one core component, that is the mining aspect. Why mining is so difficult? Well, European Union had figured out this very interesting way of living, where they are like, hey, we know, because we have thankfully figured our stuff out a bit earlier than others, that if you poison your environment, you die. They figured it out. And same with America, they figured it out. Oh, if we poison the rivers, we die. They figured it out. So what they did, put environmental protection, and they actually enforce it. Not to the nth degree, but they actually enforce it. So then they created an issue for basically industrialists, where they're like, hey, we can give you products. We can still, like, for example, clothing dye industry, those produce way too much toxin. So cotton production, not that poisonous. The moment you take that cotton, make it into threads, and now dye that puppy into different colors, the output poisonous. Now, can that be handled? Easily. But it increases cost. People want cheap stuff. So European Union started to go send that to China. China is like, okay, I don't care about my own people, as in like CCP does not care about it, and that's why. And if you ever wondered why the heck China has so much agriculture and still is in food negative, keep poisoning the water. And same with this. Does Europe have enough material that can do this? Absolutely. Heck, they have a plant also that is working. I have linked a video down below. It's just that, why don't they? That environment regulation cost per ton goes lol. And on top of that, there is another issue. Large quantity locally may not be available. So these two vectors makes it a bit difficult. And for the pollution side of things, which is, be mindful, thankfully it's not air pollution, but it's still very toxic pollution that you are dealing with. So many countries are just like, yeah, it's better to pay someone else for that poison. It's just like, hey, take this, take my money and drink the poison. It's like that. So this is a very naughty situation. On top of that, China is like locking the supply chain down. So every country started to put a mandate where they need to figure out a way to reduce its requirement. Basically, reducing its need is priority of a nations. All of the nations, India, USA, European bloc, all of them, like, we have to reduce its need. We cannot just rely on this graph. Basically, this is how in the old days people used to have like this minerals, and then China started to happen in like 1980s era, and then slowly by 2000 China is the only thing that produces it. So every country is realizing, because again, the toxins created by this sort of mining process is brutal. They are like, the fluorides are used. Let that sink in. Like, very complicated things are used. So companies are like, hey, it's better to reduce it. Now, why the heck we have such a high demand? This magnet is cool and all that, but hard drives were a very big thing, but that's gone. We no longer have hard drives. We have SSD. So, okay, that part is sorted. And what else has changed so drastically that we are needing so much of it? Motors. Like, we went from internal combustion engine, we are making transition to motors. So motors consume a lot of magnet. Even if you are talking about something that is just permanent magnet assisted, not running on it, just assisting it, like this design, and you have permanent magnet Thomson slots that is used in Tesla current versions, that is still requiring almost 1 kilogram of magnet. 1 kilogram of high grade magnet, which either would be high temperature or it would be N52. I do not want to check the price. It would be expensive AF. So the first focus is make these motors magnet free. Can we do that? Well, of course we can do that. We can start with a normal option, that is you can just use induction motor. It works. If you can reduce the gap between the stator and rotor, you can get very high efficiency, and that's how Tesla literally started. And you can still buy Teslas that have induction motors. So it's not like, oh, end of the world. It's just like, it would be better to have better, but if you do not, this is good enough. Then you have reluctance motor, bit more efficiency, bit more oomph, but does require a bit more complicated circuitry to drive those puppies, like this puppy and this puppy, but does have some benefits. And my personal favorite, which is like the ultimate motor that bitch slaps every other motor in existence, that is separately excited synchronous motor. Do not ask me which engineer named this. This is the worst name. And if you ever want to understand what it is, it's just like a universal motor that does not have brush and no magnets. Like, how? Well, have you ever studied AC, synchronous, brushless generator? Same thing. Just somebody figured out, it's like, hey, if you cannot increase the voltage, you cannot increase the amps, and you are talking about AC system, you can increase the frequency to increase the power density. Well, we have those brushless generators, and they have been working for a century, so we know how to make that. Everything is sorted. Why not just use that on a car? Solve the problem. And here's the interesting part. It is one of the best motor. Why? It has power factor of 1. From your inverter point of view, or the motor driver point of view, it's running a resistive load. That's how efficient those puppies are. The best, because again, you control the rotating parts. Electromagnet is not permanent magnet, where the back EMF is the issue. It's like, hey, back EMF issue, you can reduce the core. It's like, hey, chill, bro. You need a lot of oomph. You need that, like, you like pump energy into the core becomes magnetized, you get awesome torque, and then you're like, now you're high speed cruising, you're like, okay, core, relax. You can't control permanent magnet, but there, you got it. And you do not have to worry about backfiring, where permanent magnet assisted motor, one of the best motor. Penalty, it does require a bit more complication in terms of manufacturing. These are just sheet metals, you know, sheet metal, take it and go. This does require you to have build a machine for winding coils. So, but one of the best motor. And I'm pretty sure if somebody figures out how to make this in PCB motor designs, yeah, we are looking into a world where we're like, one time we actually used to waste magnets on motors. That will be that kind of power density, that kind of size, it will beat every motor topology. So that's the ultimate motor until somebody figures out even better or figures out how to make this in PCB design. As of now, nobody has. But the moment that is cracked, we good. And then we some other people are also hoping, because we went for all governments are acting from both sides. They are like, hey, side one, figure out how to reduce the need. Side two, figure out how we can make it environmental friendly. Is there a way to mine this puppy environmentally friendly? Actually, yes. Cost effective, no, but if a lot of people do that, maybe industrial competition allows more research to be done, more development to be done, and we can reduce the price where it's like viable. So actions are being taken from both sides. Let's see what happens in the future. But supply chain is the issue, and every country that is aware do not like this one player option. So let's see what happens in the future. So this was my presentation on basically how the heck neodymium permanent magnets are made. Basically, this puppy. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.